Welcome back to Session 2 of Digital Basics. We begin by reviewing the answers from last session's exercise. We are converting binary values to hexadecimal. From the binary weighting factors, we see that 8 plus 2 plus 1 is decimal 11, which translates to hex B, which I'll write as 0xb. Next, adding 8, 4, and 2, we get 14, or hex E. Here we find 6 binary characters, which means that we'll have 2 hex fields. And instead of converting to decimal first, we'll go directly from the binary pattern to the hex value of E. When you work with binary and hex values, after a while these 6 combinations become second nature. So our answer is hex 2E. Again, we go directly from binary to hex for an answer of CA. And finally, a binary all ones, which gives us 3FF. Another standard bit of wisdom is that digital stuff consists of logic gates, and again, this is indeed the case. But before we dive into that pile of insect-like symbols, let's take a quick look at the background of logic in general. In the broad and original sense of the word, logic is a philosophy that grapples with the slippery tangle of human reasoning, and specifically rational processes that try to arrive at universal truths. The search has been going on for as long as there were people who could argue about it, and based on the polarized state of the world now, it seems we're no closer than Plato was over 2,000 years ago. Fortunately for us, this is not the sort of logic we're dealing with here. We're extracting the simplest aspect of the broader field, sort of like taking the back off your cell phone, staring at the inscrutable complexity, and unplugging the battery and saying, well, I know how this works. Our logic is precise and definitive. No opportunity for arguments. If you want to make a cup of coffee, you need ground coffee beans and hot water. You can, of course, add other ingredients like milk, but without both the beans and the hot water, it's not a cup of coffee. The key word here is and. Alternatively, you could use coffee beans or tea leaves to create something to brew a drink with. Again, the key word here is or. And combining actions, we could use coffee beans or tea leaves to create a brewed drink as long as we have the hot water. We need either coffee beans or tea leaves and hot water for that brewed drink. We have to be careful with our categories of precedence, however. In our first example, there's not much opportunities for confusion. We can just line up our pieces and it reads the same. Coffee beans or tea leaves and hot water for that brewed drink. However, taking a different example will make lunch either a peanut butter sandwich or French fries with ketchup. From the context, we naturally assume that we mean either peanut butter and bread or French fries with ketchup. But again, let's just line them up. With our cultural background, we naturally assume this grouping. But what if our order is taken by some AI whose I part isn't as intelligent as advertised? We could end up with a sandwich with both peanut butter and ketchup, possibly an acquired taste, but definitely not mine. As we'll come to see, parentheses are an important tool. It's time to introduce those insect-like logic symbols. This is the symbol for an AND function, and this is an OR function. Here we use the gate symbols. Take a moment to absorb this. Foregoing the pictures, we'll use just the words, noting that these could be the names of electronic signals. This is the peanut butter sandwich, and this is the French fries. The OR gate says that we can have either a sandwich, the fries, or both if we like. We need to pause here a moment though. I may have given you the impression that if you come with a jar of peanut butter and activate that line, and also a couple slices of bread and activate that line, you'll have a sandwich for lunch. But of course it's not quite that simple. Activating the peanut butter and bread lines will indeed set the lunch output active, but that's just an indication that some set of lunch ingredients are present. Maybe a light is lit in the kitchen. Somebody still has to come and make the sandwich. Let's say, though, that I wanted just one type of sandwich or the other. Maybe I specifically want the peanut butter sandwich. Or maybe another time, I specifically want the fries. In other words, I would like to add a new signal called selection that will select between the sandwich and the fries. In fact, let's call it select sandwich. When this signal is active, we know that we want a sandwich for lunch, not fries. We add another input to our sandwich AND gate, which is fine. This simply means that all three inputs need to be active for the output to go active. Now a sandwich results in a lunch when the select sandwich is active, but not when select sandwich is inactive. We're not done though. When we want a sandwich, in other words, when the select sandwich signal is active, we want to disable the fries. We do this with a new type of gate, an inverter, which does just what its name implies. When the input is active, the output is inactive. And when the input is inactive, the output is active. So when select sandwich is active, the sandwich AND gate is enabled. And when select sandwich is inactive, the fries AND gate is enabled. We often use a bubble to show an inversion. Finally, we can carry our selection signal off to the kitchen to let them know what we want. We end each session with a few exercises. The answers are presented at the beginning of the next session. We go through all the possible combination of inputs and map the resulting outputs. There's something special about output M. Gate operation in reverse. This can take a little playing around.